Welcome to Module 3, PID Control in Building Systems. In this module, we connect proportional, integral, and derivative control to practical BAS fieldwork. PID is not a magic fix. A loop cannot compensate for bad measurements, weak authority, missing capacity, or a broken final element. We will learn what proportional action does when integral action helps, how windup happens, why derivative action must be used carefully, and how to tune loops safely with trend evidence and rollback discipline. The learning objectives for this module are field-oriented. You will explain the 3 PID actions in plain practical language, recognize common symptoms such as offset, hunting, windup, saturation, and slow cycling, and verify the physical system before touching tuning values. You will also learn that tuning is controlled work. We stabilize the basic response first, then add integral action carefully, protect the loop with limits and anti-windup, and document what changed and why. The core concept is that PID supports a good physical system. Proportional action reacts to current error. Integral action removes sustained offset. Derivative action can add damping, but it is sensitive to noise and is used selectively in many BAS applications. Before changing numbers, verify the measurement, actuator control direction, output scaling, limits, equipment capacity, and operating mode. This slide shows one common PID representation. Real BAS products may use different parameter forms such as gain, proportional band, repeats per minute, seconds per repeat, or scan-dependent implementation. This is why copying values from one controller to another can create serious instability. Always understand the product units, scan interval, and output scaling before applying tuning values. Proportional action creates an output change in proportion to present error. More gain gives a stronger immediate correction. Too little gain leaves large deviation and sluggish response. Too much gain can create repeated crossing and oscillation, especially when the process has delay. With proportional-only control, some steady error may remain because that error is what holds the output at the required value. Integral action removes sustained offset by accumulating error over time. It is powerful but dangerous when the output is limited or the equipment cannot produce the requested result. This is integral windup. Anti-windup prevents the controller from storing a large internal error while the loop is saturated, disabled, overridden, or missing proof. Derivative action reacts to the rate of change and can add damping to selected processes. In many building applications, PI control is sufficient. Derivative can amplify sensor noise and can behave differently depending on whether the controller uses derivative on error or derivative on measurement. Use it because the process benefits from it, not simply because the block offers it. A safe field method starts with verification. Confirm the sensor, actuator, capacity, direction, output scaling, and stable operating mode. Trend the loop before changing it. Make one change at a time. If possible, reduce integral action temporarily, establish a responsive but stable proportional response, and then add integral action slowly. Wait several process time constants after each change, and record the previous and new settings. Output limits, deadbands, rate limits, and bumpless transfer are not cosmetic settings. They change the control behavior. Limits must coordinate with anti-windup. Deadband can reduce movement but should not hide bad tuning. Rate limits protect actuators but add delay. Bumpless transfer prevents the output from jumping when a loop returns from manual, off, or another mode. Cascade control uses an outer loop to reset the set point of an inner loop. For example, a zone loop may reset discharge air temperature while the discharge air loop controls the valve. The inner loop must be stable and faster than the outer loop. Supervisory reset strategies should be bounded and should not remove safe local control if the server or a network is lost. This table connects trend patterns to likely causes. Fast repeated oscillation may indicate too much gain, a noisy sensor, process lag, or output scaling problems. Slow cycling often points to integral action that is too aggressive for the process. Stable offset can be a normal proportional-only result, an output limit, or a capacity mismatch. The table guides investigation, but field verification remains necessary. This checklist is the safe field standard. Confirm the direction, scaling, sensor, actuator, equipment availability, capacity, PID units, output limits, anti-windup, tracking, and baseline trends before changing settings. Only one tuning family should be changed at a time. Record the reason, previous settings, new settings, operating conditions, trends, and result so the organization learns from the work. Let us summarize Module 3. Proportional action responds to present error. Integral action removes offset, but it must be controlled during limits, overrides, disabled equipment, and missing proof. Derivative action can add damping, but it is sensitive to noise and implementation. Safe tuning begins with physical verification, not with changing values. In the next module, we will focus on measurement validation, filtering, and sensor confidence because no controller can make good decisions from bad data.